Just to review, this is where we're at with our model. So I'll review for a few minutes and then we'll jump into the new material. We have a machine learning framework where we want to take data X and predict things about it Y abstractly. Both of those are represented as vectors. That problem can compose many scenarios of interest. X's as images, Y's can be labels of what type of image it is, or segmentations of where things are useful, or a diagnostic decision about that medical image, or even a scientific discovery, or not, depending on what you're really interested in. Our model is extremely simple so far. It's a linear model. It maps X's to Y's via some weights W in a matrix. This matrix is unknown to start. We have to learn it. So to learn it, that process is an optimization problem where we have pairs of X's and Y's, and we want to figure out W's that optimally map between those two, right? The process of figuring out those weights is achieved by gradient descent on a loss function that tells us how much training error we have in the process of figuring out the model, W. The linear classification problem, as we went over last class, is not good. We briefly reviewed 3 reasons why. The third is that the loss function inherently depends on the data you're examining and your goals. Right? So here we just picked mean squared error because why not, right? It's a good one to start with. But we went over this example of a CIA agent versus an Apple engineer creating a cost function, ln, for the problem of performing Face ID, right? There's 2 types of error in that problem. There's the false reject, where it doesn't let the user in when it actually is the user, and then there's the false accept, where it lets a malicious actor into the phone. And you can trade off those 2 quantities in a lot of different ways, but the simplest way is just to set up a cost function that's a training error function that is each component added together, and you can add a scalar multiplier to the component that you feel is more important, right? And so here the CIA agent would think that false accepts are more important to prevent because you don't want the identity or secrets or whatever that your spies have in their phones getting out there. Whereas an Apple engineer would do the opposite because they would not want to get fired for annoying customers, right? Okay. So the second problem is that we only allowed for binary classification or binary labels. Actually, another way to say that is in the process of setting up this linear classification problem, where essentially we adopted the mean squared error and the simple model, which is a linear model, from linear regression, and then we said, hey, we have a classification problem, so we'll take the sign of each resulting W times X to make a decision during the process of establishing the optimal weights W. That process is not ideal, and we showed that if we take a step back and consider things probabilistically, then we can say, hey, an optimal model would not say, hey, this is either, like some new training example comes in, hey, this is category A or B definitively, right, via that sign operator. Instead, to say that probabilistically, you say, I'm 20% confident this is category A, so 80% confident it's B, or I'm 50-50, or I'm 99% confident, right? That's achieved with this logistic function. The logistic function takes the input, or any input, but here the input is from the model for a given example n, and that number can be anything, right? And instead of just saying, hey, it's either going to be -1 or 1, right, casting to those 2 decisions, the theta function maps to a continuous distribution between 0 and 1, right? So a probability measure. So if you insert that gentler approach into this framework of analyzing our linear classification problem, it becomes what's called a logistic classification problem, or a logistic classifier. So this logistic classifier, instead of using mean squared error, we derive pretty easily by saying, hey, we want to maximize this probability of the labels being correct given the input images. Take this expression and try to maximize it, where the theta function is defined over here on the left, and the input is we carefully designed to be the label times W transpose. So you just crank the wheel and you get this cost function here, this in-sample loss function or training error loss function, which is just a different expression, right? It's called cross entropy, and it's the most popular loss function to use in classification problems, right? So by default, if you start playing around with classifiers, as we will in this class, or if you just go online right now and do it, that's what's going to be used, is that loss function, okay? And so that's a better one for classification problems in general than mean squared error. There's lots of loss functions, right? You can add different things to this and manipulate it as you like. That's the basis of a lot of modern machine learning efforts. So that was the second issue. And then the first issue is obvious, right? We've talked about this a lot of times. Linear classifiers are rigid. They only allow you to draw planes between your data points of interest, right? And so the planes or hyperplanes can naturally not curve or encompass other deviations that would be allowing you to better classify your data or section it up however you're trying to. So here we have a classifier, W, right? It's a linear classifier. And we said, hey, maybe there's just not enough weights in there. Can we just add more weights? Will that make it better? And the answer is not really. It'll add more numbers to optimize for, but you'll still be left with solving for a hyperplane, right? Because if you just insert two linear matrices next to each other and multiply them, you're left again with a matrix that's still defined as a hyperplane. Okay, so you can't just add weights or add cascaded matrices. Instead, what the inside of neural networks is really, you do that and you just add a nonlinearity between the matrices. So that's it. That's what a neural network is, as we'll get into more and more, but it's simply just adding a nonlinearity between cascaded matrices that map your data to your labels. Okay. What is this nonlinearity NL? Here I wrote it's the maximum of the value or 0, which is a ReLU, rectifying linear unit, which we drew before. The max function 0, comma x. People also call that just the ReLU of x. ReLU stands for rectifying linear unit. Well, kind of a mouthful. So is ReLU actually. I don't know. You can call it whatever you want. This is a normal nonlinearity that's pretty common, but it could be another nonlinearity. It's just like the absolute value. Hundreds to pick from. Okay, and so then we can add more. We have no reason just to stop with adding two matrices with one nonlinearity between them. We can add 3 or 4 or 5, right? What's the point of stopping at 2? That's an interesting question. So that's what we'll discuss today, right now. So this is a picture of a convolutional neural network. I'll define that later in the class. I just wanted to show you this because essentially what we have in these types of network, which is what we're working towards, is a linear operation, which you can define as a matrix. That's a convolution, right? And then a nonlinearity. Then there's another convolution, so another matrix multiply, and then another nonlinearity. And you repeat that several times. Okay? And at some point, one decides to take the convolution matrix and replace it with just a full weight matrix. And so essentially what we're working towards is a model where we have here 5 linear transforms, linear matrices W. 3 of them are convolutions, shown 1, 2, 3. And then 2 of them, which is called fully connected, are just full normal weight matrices. So the weight matrix we've been talking about so far, without any restrictions based on it. And that's it, right? So it's really not that complicated at the root of it, right? It's just a series of matrices with nonlinearities between. These pictures make it seem more complicated than it actually is. And there's all this terminology we need to get used to talk about these matrices and their different properties. Okay. In picture, if you've been reading about machine learning or trying to Google about it, people now draw like really complicated diagrams that have lots and lots of these linear and nonlinear transformation pairs. This is maybe 20. At some point, it becomes not necessary to even define all the little properties of them because it's just a series of these interleaved operations, and they get so complicated that it's better just to download a setup that someone else has put together that just works well. Okay. So the goal of this class is not to get really good at creating these and tweaking their numbers and everything. Other people have already done that, so we just adopt what they've done. But we'll get into that later. So before we really start talking about complexity and this idea of learning models that can be more flexible or slightly, curved or to highly curved to better capture our data, the first question that is useful to consider before getting into that is, can we just avoid this problem of making models too complicated up front, right? Instead of just jumping to the conclusion, hey, let's add a series of linear and nonlinear transformations, should we maybe consider something else? And the answer is there is something useful to consider, and that's this coordinate here, x. Right? And so this idea of, hey, we have a linear classifier, is there something else we can do to make it slightly more flexible, has obviously been thought of a lot in the last 50 years. And a big focus of machine learning was to do coordinate transformations on the input data to try to adjust this problem. And so here's a simple example where we have some data that is very hard to classify using a linear classifier, right, on the left. And by simply manipulating the coordinates that define the underlying data by here doing a polar coordinate transformation, you are able to easily separate it with a linear classifier. Right? So this is obviously a trivial example to highlight a point, but the idea of playing around with the coordinates that we're working in to start is really probably close to home for some of you on your homework right now, right? Because we have these images, there's 784 dimensions, right? We're reducing them down to 2, and we suggested using intensity and symmetry to do that, right? And there's different ways to define intensity and symmetry, but also you could just not do intensity and symmetry. What if you picked some other way to summarize the data? Or what if you added a third coordinate, like intensity, symmetry, and whatever, thresholded sum of pixels. So you pick up really bright or really dark pixels or something like that. I'm just making ideas up. But there's lots of other things you could try to add or manipulate the underlying dimensions of the classification problem. And so you've probably maybe played around with that and have seen that, yeah, if I define symmetry one way, the data gets a little bit more separable than another, right? And so this idea has been around a long time, and it was essentially the approach to execute machine learning methods even when I was just starting grad school. So before convolutional neural networks really took off, a big focus of machine learning, where we were downloading like 1 million images that were each 32 by 32 pixels, was to essentially establish effective coordinate transforms on that image data to then enable effective classification using standard like logistic or other classifiers, so not complicated classifiers. And so a simple way to do that would be to say, hey, instead of just taking this frog image and trying to multiply it into a matrix and then seeing what happens, let's take a color histogram. Right? Different frogs have different colors, and if we pick the right histogram transformation, then maybe I can pull out this type of frog, I don't even know what this type of frog is, from like toads, which are browner, for example. You could also measure gradients within the images and say, hey, I'm going to first measure all of these spatial gradients and then look at those gradients and how they're ordered. Tree frogs are more bendy than toads, which are rounder, right, for example. Right, so all of those are inherently driven by our own intelligence, right? It's like a human established insight into the problem that's trying to create better coordinates. And those general techniques probably led, I would say, the most effective use of them led to a lot of really pretty effective machine learning work in 2008, 9, 10 that went under the name of bag of words. So in this approach, you would essentially take lots of patches from an image and create a dictionary that we had created for our spectral unmixing problem, and then use that dictionary to establish a new basis that is much lower dimensions than the actual images to then begin to try to classify. And so here you take patches of cats and frogs and establish a new basis, a functional basis, right? So this, for example, would be similar to your symmetry calculation right now, where these would be positive values, these would be negative values, and you're essentially multiplying that by your image and then adding up all the pixels, right, for example. You do that maybe across 20 different dimensions, reducing the 784 pixels down to 20 dimensions, and then you would map every new image into that lower dimensional space before trying logistic classification or some other simple classification. Okay, and so the take home of that is it doesn't work well, right? Which is a bit surprising. So that's why everyone has adopted convolutional neural networks, and that's why we're going to work with that in this class, simply because it works better. But it's worth thinking about because the approach where you apply human intelligence or some sort of traceable statistical analysis to your large data set to first extract features or establish some new dimensions to work in to then classify does not work as well as just letting the computer figure out that space by itself. Right? So saying, hey, computer, just apply a lot of linear and nonlinear transforms, and within the early parts of that, you will have created a new lower dimensional space, right, that then we'll try to classify with. That simply works better, but it's very black box, right? I want to make sure everyone's aware of that. This lower approach gives us less insight into what's going on. But here, at least, we can try to figure out better ways to change this feature extraction box, tractable ways. The frogs aren't that yellow, so the feature is going to pull out more purple or something, right? Because we have visually observed that's more important in the data. We can't do that here, and what we're going to switch to, okay? And it's actually a better idea not to do that if all you're interested in is performance. And then the other thing I wanted to highlight is how this connects to some of the topics we were talking about earlier in the class, specifically about designing hardware to achieve certain effects in imaging systems. So if we had a camera and we said, all right, let's take a picture or a set of pictures of some letters, for example. Now we want to classify those letters, right? Or you're designing an imaging system to take pictures of the MNIST image, and you tried to classify it, and on your homework you saw it didn't work very well. You could then say, hey, well, maybe a better camera, I can design a better camera to better classify those images, right? I can add some sort of mask that we've discussed already to change how the image is blurred to potentially highlight E's versus O's or some preset letters that you are working with, or numbers right from MNIST. And that process of pre-designing the mask, you can use your own intelligence to say, hey, E's have more lines than O's, and so perhaps there's a mask that highlights those features that are horizontal and vertical versus round shapes. But the approach that I showed below is saying, hey, don't use your own intelligence to do that. Instead, perhaps there's a way to use a machine learning algorithm to simply figure out that a mask that you could use such that when you do capture an image and try to classify it, the resulting classification will work better than any system without it. So how can you, in your approach of optimizing a machine learning algorithm, also consider how the image is captured to then drive that performance even higher, right? The answer to this problem is yes, that this does work, but it is obviously really dependent on the data you're capturing, what it specifically you're looking at, and yeah, the imaging system you're working with. All right, so now we're going to run through statistical machine learning in 30 minutes. Okay, and so really there's two goals when we're doing machine learning, and we've already talked about these a bit. And so the first goal that we are focusing on in our effort, so 90% of your time on the final project and probably 95% of your time on the final project will be this first goal. And also in your research, if you're doing research on machine learning, or even when you go work at a company and try to create a new machine learning model for whatever data is given to you, you're trying to minimize this in-sample error, right? ln, during training. Right? You really want to find a good approach that allows that in-sample error to decrease as the algorithm keeps iterating in its search for the best weights to use to classify your data. The second goal that's really actually more important is to establish an out-of-sample loss function. So this is the loss function that's defining how well you're doing on your test data that is close enough to your in-sample loss function. And so another way to say that is you're going to have data and you're going to try to classify it as best you can. What's really important is, does it generalize to your test data? Does the model you've established effectively allow you to classify unseen data that's out of sample, right? Out of the algorithm's view during training? I took a class on statistical machine learning, and we essentially assumed it was not possible for half the class, right? Because essentially I think that's how the field developed. It was an unknown question whether or not you can effectively create a machine learning model that does generalize to out of sample data. So you can do it, obviously. That's why we have machine learning tools in our computers now. The out of sample error will never be better than your in sample error, right? So you have to get comfortable with that. In other words, when you train a model, it might not work perfectly, or it probably won't work perfectly, and there'll be some error left over. When you go apply it to new unseen data, don't ever expect you're going to get lower error than you did in training, right? Because during training, the algorithm has all the ability to see the data, right? And so it has all the ability to cheat and try to move its separating lines however it wants. And you can't expect it to do better if it has never seen any data points before. These are all from mathematical insights from 40 years ago. But the bound shown above will grow with model capacity. So I'll explain what that means in a second. But essentially, as we allow models, our machine learning models, to become more and more complicated, right, have more and more nonlinearities in them, the bound between what we can say we're going to get during testing versus training gets worse. Right? So the idea of using neural networks with tons and tons of weights is actually not intuitive at all. That's why it wasn't really considered, because mathematically speaking, it should do worse than a simpler model. But the last point is really important. This bound shrinks the difference between how well you're going to do during algorithm training and testing as you get more and more examples, right? And so this is what has enabled modern machine learning to work, right? People didn't consider neural networks, really complicated neural networks, as an effective solution for a long time because this bound gets larger and larger as neural networks get more complicated, right? Testing is, you're going to do worse when you try out your neural network on new unseen data. But what happened was modern computers were able to see not just 50 or 100 or 1,000 examples, but 1 million or 10 million examples. Difference really pushed their performance over the edge. What do I mean by model capacity? What does that kind of refer to? And so essentially, model capacity is just how complicated is your model. And complicated you can mathematically define just as a polynomial to the nth degree. And so a simple model is a linear model. It's a first order polynomial. A more complicated model would be, let's say, a 10th order polynomial. So this would be constant plus ax plus bx squared plus cx cubed up to x to the 10th, right? Yeah. Here are some data points. And instead of drawing points that I'm trying to classify for right now, it's just, can we fit a line to these data points? And this might be my training data. It's a bunch of points. And I'm going to say, OK, I'm going to train my model to figure out the best line to fit across these points. And it can be a 10th order polynomial. And you'll get this, right? It looks great, right? It fits all the points perfectly. Here's the test data set, right? Is this going to work well? You could just get super lucky, and maybe it does work well. But chances are that your test data isn't going to look like that given training data that looks like on the left. Chances are, just from the law of large numbers, where points approach Gaussian distributed blobs, your data is going to look like something on the right, and your line of best fit isn't going to work at all. Right? So a 10th order polynomial was too complicated to use. Why? Because you didn't have that many data points to begin with. So the complexity of your model does depend on how much data you have for your training process. That's generally not a concern anymore because of modern machine learning, we have thousands and thousands of examples typically. But if you don't, then you should think about that and say, hey, maybe I need to use a simpler model to start. And by simpler model, I simply mean like a second order polynomial, right? So a slowly curving function, right? Like a plus bx plus cx squared type fit that doesn't work well, quote unquote, on your training data, right? Certainly not as well as the 10th order fit. There's a lot more error in those points, but it does generalize better to your test data, right? And so model capacity is simply a term that's used to describe that n in the nth order polynomial. As capacity goes up, that number n goes up, right? And so people say capacity, I generally think complexity, right? Model complexity being more complicated on a 10th order fit, more wiggles, right? And less complicated on a second order fit, right? Less wiggles. Okay, and so what you'll observe when you perform or start looking into machine learning methods is that there is an optimal setting for the complexity of a model. As you increase complexity, you'll see error quickly drop. If you tried, instead of a plane or a hyperplane to separate your data, said, I'm going to solve for a parabola or a cubic or quartic function, for example, your error is going to rapidly drop and you're going to get much better performance. As you then go higher and say, oh, that's great, I'm just going to go to 10th, 20th, 30th polynomial fit, you'll then see your model do even better on training. We've seen that picture of the lines, like really carefully separating the red and green points with lots of curves. But we get what's called a generalization gap. So during testing, you're going to do worse, right, as you keep making it more and more complicated. Why is that? It's because of what I just showed up there, right? This really complicated line does not fit these great points as well as the simpler one. And so there's a sweet spot, and we need to find that sweet spot. One of the multiple points that needs to be considered as you're setting your model up. Okay, and something that is more theoretical but worth mentioning because we're going to return to it in a few minutes is this idea of a hypothesis space, right? And so the hypothesis space for your model is the set of all possible functions that you could try to use to separate your data. As you go from linear functions to polynomial to higher order polynomial functions, that hypothesis space increases in size, right? There's more possible parabolas in the world than linear lines, so to speak, in some mathematical perspective of what we're talking about. Okay, and so these plots are important because they really drive home this message and highlight a couple things that are going to define ever-present sources of errors in your machine learning optimization endeavors. On the first plot, I'm showing a low capacity model. So this is like a linear classifier or slightly more complicated classifier. As you've already seen on your homework, during training, you're left with a relatively high error, right? You have, let's say, 90% or 80% or 70% correct, but a lot are incorrectly classified still. Why? Because that line can't bend to separate those X's and O's, so to speak, the handwritten 1s and 5s that you're working on. When you establish that final model, you're then going to test it. And what you'll see is the testing, especially if you go to the limit of having lots of data points, so trying to separate, let's say, 1,000 handwritten 1s and 5s, the test error will almost exactly match the training error. Why? Because the lower complexity model generalizes really well to the unseen case, the case where you haven't seen the images. Right? So that's great. The error is high, but at least you know how well it's going to work in the real world. The second option is to say, I'm going to make my model more complicated. Not just do linear classification, but something more complicated. If you let it get really complicated, then during training, you can have a much lower error, right? You can get like 99% of all your data points correct, especially as you have lots and lots of data, right? To allow that really sharp curve to carve itself between the X's and O's. What you'll see is your test error will not ever decrease to the point of the training error. Right? This is this generalization gap. When you have this really complicated set of wiggles for your test data, it can really separate them well, but when you try new unseen data, it won't work that well. Right? Because you made too many small wiggles to try to carve out those two sets of data points. So that's what you want to avoid. And you'll see this on your homework and your final project. You'll train, you'll think things are going great, and then you'll test, and things won't work. And this is one reason why it might not work well. Okay? And this is just not anything to do with you or your code. This is just foundational math telling you that you have to be careful about how complex your model is and how many data points you have to train and test. Okay? The takeaway concepts. Your test error, like I said before, will never be less than your training error. Right? The test error can only asymptotically approach the training error in the limit of many data points. Complicated models appear to do better, might end up having really great results, but if you're not testing, you're going to be stuck again over here. And then the third message is, if you don't have enough data, that's a problem. When in doubt, try to get more data. That's a basis of modern machine learning. More data is better. Okay, and so this leads to two important theoretical concepts I just want to introduce. We're not going to dwell on them in this course, but this is really the foundations of statistical machine learning. If this is of interest to you, then I'll give you a link in a second to some really great material online. And these two terms are called model bias and model variance. And so model bias and model variance are the two sources of error that will make your machine learning method not work perfectly. They summarize all of the reasons why you're going to end up with whatever performance you end up with. 90% accuracy or 80% or whatever. Model bias is defined as the distance between the model you've established that you think is going to work really well and you're going to deploy out in the world to classify all whatever cats and dogs on the new iPhone, and the actual true model that does classify all those points, right? And this foundationally is a theoretical exercise, right? It assumes there is a perfect model, G, that can classify all cats and dogs images, for example. And your model F is going to approximate that. It's never going to be exactly equal to it. It's going to be away from it a certain distance, that distance being the bias. Okay, and so I sketched that here. The learned F is, let's say, not so complicated. It's this blue curve during training. The actual true model that classifies all the images of cats, the red circles, and dogs, the green circles, is this more complicated curve. And the bias is that kind of distance between those two models. And so it is a mean squared error distance, a Cartesian distance in reality. The second concept is variance. So variance is the size of the hypothesis space. It's the distribution of all possible functions that can separate your data, right? And so instead of just having one G, there in reality is many possible functions G that can separate the images of cats and dogs. And if the complexity of the model that can separate all images of cats and dogs is lower, there's going to be less variance. There's less possible models that are linear that can separate the green and red dots. Whereas if I let it be all 10th order polynomials, this will get large because there's lots of possible 10th order polynomials that I can draw with little wiggles in there that'll separate the red and green dots. Which one is the best? I don't know. That's the problem with having too complicated of a model. You're allowing the variance of all possible models that can work to get larger. Right? And so that's not great either. Okay, and so the bias is responsible for the error you're going to observe during training. You're going to try to find the best possible function to separate out the green and red dots. You're not going to arrive at the optimal one. That distance is going to be your training error. And then the variance is going to tell you how much error, in addition to that bias error, because when you actually test things, then you're going to see unseen data. So how can you expect the algorithm to do better during testing than training? The variance is the remaining error. Right? And so if you allow your model to be too complicated, then the variance is going to be large. So you'll have, during testing, not just the error due to bias, but also a large variance error. Right? So that's, in other words, variance error is the residual error that you are going to incur for making your model too complex. And so you want to avoid that if you can. Sometimes that's hard. Right? The sum of the bias and variance defines your final performance. Right? So when you go and make your machine learning model and then test it and say, I have 15% inaccuracy or 20% inaccuracy, that's going to be due to bias. Some of that's going to be due to variance. You can tell, you can figure it out because you see the error during training. So during training, I had 10% error, 90% accuracy. That's your bias. And then you got 5 additional percentage points of error because when you tested it, it had 15% error. And that's your variance. That 5% is your variance. Right? And so you can see bias and variance, or rather variance, will decrease with the number of data points you have. So that's good. If you get more and more data, you can beat the variance down. Bias will always be there. Just because no model is perfect. Or you can't make a perfect model. All right, so any questions about that? I know it's a little of an aside for a lot of the stuff we have been talking about, but I just wanted to find the 2 main sources of error that you will have to live with. There will be additional sources of error. For example, bugs in your code, right? Misclassified data for training. I don't know. Poor gradient descent performance, right? Getting stuck on a local minimum, etc. But these 2 are unavoidable, even if you smoothed everything else out. All right, so how do you formally define these topics? The short answer is it's pretty complicated. And so that's why I'm not going into it in this course. But a really good course that I took that does get into it is a YouTube link is here. If you just Google learning from data, there's a whole web page and lecture notes, and a book, actually, a really good little 50-page book that is great for even like the non-mathematician, I'd say, non-specialist. So it really is a good lecture and book for everyone in this classroom, like at your level. So yeah, I'll just leave it at that. So the real conclusion is you want a model that is complex enough to capture variations within that high dimensional space, right? To carve out the red and green circles, but not too complex. You don't want to overfit the wiggles. So you want the model to not wiggle too much because you want it to generalize, right, to unseen data. You can start to measure the complexity of your model and really understand it for lower dimensional or less complex, lower capacity models than what we'll actually be working with deep neural networks. So if you are interested in exploring this, you can create simpler models and really understand their complexity and start to add, rather their capacity and add capacity, to them via extending the number of polynomials that they're able to encompass. But for deep learning models, a lot of this theoretical stuff not only gets swept away and is intractable, but also leads to questions that are still not resolved, right, from a theoretical perspective. So here's a few counterintuitive properties that deep learning models have effectively unearthed that go against a lot of the conventional wisdom in statistical machine learning. So first, you could just try this, but deep learning networks can work well on images with completely randomly assigned labels. So even if your underlying data has very little structure, right, the deep learning models can really carve out and fit between those data points, right? Their complexity is so wiggly that it can separate any data point during training, right? And so what can happen is you can train models that appear to be perfect, and then you cannot expect them to generalize at all, right? And you're in a new regime where the training error can go to 0, and then you're going to have a huge amount of test error remaining in certain scenarios. The second weird thing with deep learning networks is that as you make deep learning networks have more and more weights, longer and longer chains of linear and nonlinear interleaved operations, they can actually generalize better, right? And so that's a little bit different than what I was saying. If your polynomial fits too wiggly, it won't generalize. It turns out that if you use convolutional neural networks and cascade a lot of those operations, it can actually generalize better than fewer convolutional steps. Right? Why is that? I don't know. I don't think people know, but it's just a kind of empirical finding that people have figured out. But it's specific to convolutional neural networks, as far as I know. Okay, and so the third kind of tricky thing is that complexity, this idea of capacity and complexity, how complex a model is, isn't just, I've been saying, oh, it's this nth order polynomial. In reality, it also depends on the loss function you select, right? And the type of optimization procedure you're using, right? Which type of gradient descent, for example. What's the step size, all that. All of that you need to account for as well, right? Which is swept under the rug in statistical machine learning. It's more of a theoretical exercise, just saying, you can find this model somehow, as opposed to actually being engineers and implementing the optimization procedure to find it effectively and in a reasonable amount of time, not iterating for a week. So the last 2 points I wanted to make are, well, the first point of the 2 that I wanted to bring up is called the no free lunch theorem. And so this is a theorem, right? So it's pretty important. There's not that many theorems in machine learning, I feel. There's too many bendable, flexible rules. But the no free lunch theorem says that average over all possible data generating distributions, every classification algorithm has the same error rate when classifying previously unobserved points. Right. So that means another way to say the no free lunch theorem, at least I'll try to summarize, is that it doesn't matter how complicated your machine learning algorithm is. A simple one will do just as well as a complicated one. The key term here is when you consider all possible data generating distributions. Right? So what does that mean? All possible data generating distributions means every possible type of data set, right? And so that is not useful to consider when you're thinking about images. So images, if you consider all possible images that could ever occur, right? That means you're in some 784 dimensional space, like your MNIST images, and you just randomly select a point, or you start to randomly select points, right? That's forming some first data generating distribution, and then you can randomly select some other points. What you'll get if you just randomly select a point in 784 dimensional space with almost one probability is an image that looks like this, right? For example, this has more pixels than 784, but I'm just showing you an image of Gaussian noise, right? So if you just select a point in the space of all images, you're gonna get this noise you maybe have seen on an old TV, right? I don't know if anyone is old enough to have seen that, except me. No underlying structure, right? And so that is not really an image as we think about it. It's just kind of noise, right? In machine learning, a lot of these theorems and things work in or are considering data as general distributions, which is like this. And in imaging, we're not really interested in this. So you have to take a lot of these statistical machine learning insights with a grain of salt. Right? Because what we're really interested in are images like this over here, where this is a bunch of faces. And this particularly is showing a generated face that's sampled from something called a manifold. Right? So these ideas of manifolds have been around a while, but I think are more and more relevant now. So what's a manifold? So a manifold is... I'll just adopt this. This is some 784 dimensional space, right? It's hard to picture. Right here I'm drawing 3. A manifold is some particular carved out space within this 784 dimensional space that defines the space of all face images, for example, or defines the space of all images of little cats, right? Or whatever you want it to be, or all images, period. Right, that look realistic to humans. It's a much lower dimensional curve. Here's a manifold drawn over there, a one-dimensional manifold drawn in a two-dimensional space. And that's really what we're after, is thinking about those manifolds in machine learning. Why? Because we only care about images. CT reconstructions, for example, form one particular manifold in that space. Microscope images form another manifold, right? Those manifolds probably don't intersect. What are their dimensionalities? What are their properties? It seemed out of our reach to figure that out. But I think now we're at that point with generative models that we're able to figure out these manifolds, right? So we're at the point now that because we're able to effectively train certain machine learning methods, we're able to start to form these manifolds that we can navigate across digitally. Right? And so here's an example of navigating through the space of possible images of faces, right? Which is essentially sampling from some manifold in, 1024 dimensional space, because these are probably 32 by 32 pixels or whatever the number is, and being able to generate realistic looking images of faces simply because we're able to make sure we're on that manifold picking out points and not off of it. This idea of, manifolds we won't really get back into until much later in the course. We'll talk a little bit more about generative machine learning methods towards the end. But it's useful to keep in the back of your mind as you're thinking about your networks, some of these statistical machine learning insights, and how they are generally useful, but also not particularly guided towards the problems that we're considering, where our input data generating distributions are very specific, right? They're not just a general all points in 784 dimensional space, but a very small manifold that we want to leverage to make our machine learning methods work. Otherwise, they wouldn't. So yeah, next class we're going to dive into convolutional neural networks. Now that we have at least some understanding of why your methods might not work that well. Theoretically, there's other issues to consider too. All right, thanks everyone.